So let's start. Okay, I don't know how much. I'm not sure how much sense it would make without the background for you, but hopefully it would make some sense. So what we were trying to do was, I suppose you at least know the topic, right?
Yeah.
Okay. So yeah, so we're basically trying to show that there exists an oracle such that QMA, so that's the informal statement, that QMA equals BQP relative to the oracle, and at the same time there exists a pseudorandom unitary family relative to O. That's the statement we're trying to prove. Okay, so last time we looked at, we were trying to give the construction for how you make this oracle. So the oracle consisted of two parts. So there was the quantum part, and then there was the classical part. So the quantum part we already discussed last time. So this was just a sequence of unitaries where each UN was essentially a direct sum of 2 to the n different n-qubit hard random matrices. And I think Uttam had asked last time whether how one would access these unitaries, because it looks like there's 2 to the n of them. And the point is that you can think of it as follows: that you ask, that, so suppose you write un as let's say u1 to u2 to the k, 2 to the n, okay, and k is a string in 0, 1, n. So to the oracle, you give it k and you give it the psi, the vector on which you want to apply the ith unitary. So this is n qubits, and so then un acting on this would behave essentially as identity tensor u sub k acting on. Okay. So that's how you access it. So because it's essentially like a control knot, right? Like, so control knot 0, 1, it's a direct sum of just 2 unitaries. When you have many, you just make it a. So okay. Is that okay? So the question, Uttam's question was, how would you access 2 to the n different unitaries if you're bounded in the number of queries? And the answer is that you can index it by saying that I want to apply the kth unitary on my n-qubit state, and then the unitary will act like that. Okay, so that was the oracle, the quantum oracle, and we are yet to define the oracle C, and this part is a bit non-trivial. So let me write it down, and then I can give some intuition about what's happening. So a classical oracle, right? One can think of it as a language, essentially, right? So here are some quick remarks about this language C. So C is defined deterministically and independently of U. Okay, so the language is fixed, it's independent of the first oracle. So that's the first point. The second point is that C is defined in 2 stages. Okay, so the first stage is that not 2 stages, it's defined in stages. So we first define on 1-bit strings, okay, and then using this we'll define it on 2-bit strings and so on. Okay, so that's how the construction is going to go, and so that was the sort of the story part. Now what the actual definition says is the following. So for a string x, define Cx to be 1 if all the following hold. Okay, and what are the conditions? So the first condition is that X is a description of a quantum oracle circuit V U bar C acting on psi that takes as input the quantum state psi and queries U bar, which is quantum, and C, which is classical. Okay, so X here is being interpreted. So X here is being interpreted as the description of a quantum oracle circuit. Okay, and what the circuit does is it takes as input these, the quantum and the classical oracle and the input psi. So it's sort of imitating the QMA verifier, right? Because the QMA verifier is expected to get a witness and has access to the oracles. So this is just giving a description of such a verifier. Okay, but crucially,
description is, I mean, this oracle circuit, oracle is black box, right? So what does it mean that I'm giving the description of the circuit?
You say apply this unitary, apply this gate, apply that gate, and so on. So it's just a description of the circuit. X is a description of the circuit, the quantum circuit.
Description of oracle is.
It's not the description of the oracle. I'm saying this is the input that is given to the oracle. So you're going to query the oracle using some input, right?
Yeah.
So what I'm saying is that this input is to be interpreted in this format. The format being that this X is actually describing a quantum circuit.
Yes. So what is that quantum circuit?
It's arbitrary. You can come up with whatever convention you want. I'm not going into the details, but you can say, you can specify qubit 5 and qubit 3, apply a C naught or whatever, and so on. So you just describe gates and the qubits it acts on, and so on.
What is the circuit supposed to be?
What is the circuit supposed to be? So the circuit is going to, basically it's just describing this circuit, right? That there'll be some X gate, I don't know, some C naught, whatever. So you have a bunch of these wires, and then at some point it will query U bar, at some point it will query C bar. Oh, sorry, not C bar, C, right? So you're just giving it a description of this circuit, and you're saying it that it's supposed to run on this input. Okay, since it's a circuit, you have to start from psi here. So it's just describing what the gates are and how to apply them. Does that answer your question?
I'm just saying that so X is arbitrary length system.
Yeah, but you're polynomial, so you won't be able to give a, I haven't described, when I'm describing the oracle, I have to describe it for all inputs, but of course efficiency considerations will appear later, because you will not be able to access everything, right, in an oracle.
Let's see how.
Yeah, but the definition at least is clear, right? Any other questions?
C is the language.
Yeah, so we're defining C at the moment. Yeah, language oracle, it's the same thing. Yeah. It's a classical oracle, so we can think of it as a language. Yes. Okay, with me so far? Is it making sense? Yeah, so these are just queries to the oracle. We haven't defined what they are. We are just saying that's what I actually was going to write. So let me write this down. So note that psi and U bar, it will become clear in a moment, okay, are not part of the description of V, the circuit V, okay, they are just inputs. Does that answer your? So basically, it's just going to say that this is the oracle, and it will describe a circuit with whatever gates, and it will leave a placeholder for the first input oracle, second input oracle, and so okay. But C is so C is going to be recursive, right? So you have to be careful because we're defining C and we're using C itself in the construction, so you have to be a little bit careful. So they're going to put more constraints to make sure. So this is why they put this statement that you're going to use C defined on inputs of length less than the one you're defining it for now. So there's no recursion. So let me make some space now. Okay, the second point is V runs in time at most okay. So in particular, this means that C queries V queries C on inputs of length at most x minus 1, right? Oh, so V doesn't look like a V. My handwriting is not the best. Okay, so this is an assumption on the so this language is defined in this way. So there are these restrictions. It will not run x for longer than this time. So that automatically means that the C that you could access would have only depended on the evaluations of C for length less than x minus 1, right? Okay. And then third is that the average acceptance probability okay, when you view it as a QMA verifier is greater than half when averaged over U bar from the distribution D. So D is this so this distribution is what we were calling D for the quantum oracle. Okay, where you have like for every n it's a direct sum of unitaries, 2 to the n unitaries. Okay, so formally this means that U bar drawn from T, you pick the best witness, okay, and the probability U bar C acting on psi. Okay, so this object is strictly greater than half. So basically it's saying that x is in the language if the verifier being described by little x, okay, with satisfying the constraints, is such that if you gave it the best witness, okay, and you averaged over u, okay, then the output would be at least 1 with probability. Output will be 1 with probability at least half. Is that okay? Is the definition clear? Okay. Yeah, it's a little bit delicate. I mean, these things are, I don't know why they're always so. Okay. Right, so we have that, and then here are some quick observations. So the first observation is that condition number 2 guarantees, right, that, which I already sort of mentioned, guarantees that C is not defined recursively or circularly as it's written in the text. Okay. So because condition 2 implies that condition 3 depends only on the previously constructed, depends on C, parts of C that have been constructed previously. Right? So condition 2 is saying what? Condition 2 is saying that you cannot access C beyond x minus 1, right? And then condition 3 is using C, right? So if it were the case that this V was also accessing C at lengths x, right, then what you're trying to define would become recursive, would become circular, because you're trying to define what x is of length n, say for example, belong in the language, and to answer that you're already using the specification of C at length n. So that's not good.
So what is U-bar length sample? Like what is
This D is the distribution that we defined for the quantum oracle.
okay.
So it's independently sampling it by itself.
And actually the statement just says C of x is 1 if the conditions hold. Right?
Yeah. So it's defining membership in the languages.
So if condition 2 doesn't hold, it probably just means C of x is not 1.
I think it could be 1, right? It just says that if the conditions hold, then it's 1. But it could also be 1 for other reasons, right? I don't think that. Yeah, but the language should be defined for all x's.
So for those
But maybe let me check if it's if and only if. Let me double check. Did I get it wrong? Yeah, I think one can just look at length and length L slices, and then I suppose it would be clear. Yeah, it just says if, but wait, to say your question again, what was your concern? That if any of these conditions are false, then the value it assigns should be 0, right? That's what you were.
Yeah.
Yeah, yeah. I don't think it says anything, right? Because it could be that.
But since it's a language, it should be defined for like all x and 0 and stuff.
Doesn't it only mean that you cannot query C?
No, it's not a promise problem. It's a language, so you can query it at all x's, and it will have a 0, 1 output.
No, the second condition says that you cannot query inputs of length higher than that.
Yeah, no. So I think what he's asking is, what if you give it, say for example, if you give it an x that does query, you give a description of a circuit that is querying say x many times, then in that case, how do you define the? Yeah. So maybe it can be interpreted as C not running V beyond x minus 1. I think maybe that just fixes everything. So like even if you give it a longer circuit, it will just not execute it. So I think everything is still fine. Right, I think everything else is okay. Yeah, and I think otherwise you could define it to be 0 as well. I don't think it would make much of a difference. Yeah, I think you could define it. I think both are fine because we're not really Yeah, I think we'll just assume that 1 and 2 are true, and then use 3 to do our actual work. Like that's how it's used in the proof. So we give x's by construction that satisfy 1 and 2. Yeah.
It is like do a promise.
Yeah, you could treat it as a promise, but the point is that the language is defined. So just I think it's just allocating, assigning 0 to where it would be perp otherwise, yeah, or bot otherwise. Okay. Any other questions?
Each thing in C describes some verifier, and this verifier, like this description of the verifier is like equivalent to the description of some language. So in the sense, like C is just capturing.
The verifier is not quite equivalent to a language, because the verifier is going to take, it's going to take a quantum state as input, which is not specified. So that's the one extra subtlety. And also it's a quantum algorithm, right? So it could output things with some probability. So you have to define a threshold. So both those things are taken care of. So they're maximizing over psi, and they are putting the threshold. But yeah, otherwise you're right. It's basically just using x2.
Converting QMA to simplicity.
Yeah. So it somehow, So this basically the way to think about it for me at least was that this language is somehow allowing you to say something about the verifier, but using a u that is different from the u that you would get in the actual oracle, right? So it's just independently sampling a u and running and giving you whether or not you get yes with probability half or not. So it's helping you run some kind of a QMA verifier, but you're not able to run it on exactly the quantum oracle you were given access to. That's the point. Okay, any more questions? Okay, let's move on. Right. So condition 2 ensures that there's no circularity. Okay, the second one is something that I sort of already mentioned, right? So we used u bar in the notation, right, to emphasize that u bar is only used on average, only used to take an average. Take an average in the definition of C, and is not the same as u.
So if I understood correctly, so
Okay.
is it like recursive in some way that so for example, if I want to run if I want to check a n-bit string, if it is if C of x is 1 or not, so does this assume that I already ran all the strings below n length?
It doesn't say you ran it. It just says that the language is defined. So because you're going to, since you're an n-bit string, you could potentially have queried it n-1 times, right? That's what condition 2 allows. But to specify the language, the response to the queries of length strictly less than n, you have to go through this procedure, right? By u meaning the definition of the language. So the oracle already has done all of the work for you.
Then I don't see the problem, because
The problem with?
the problem that Shreyas was asking, that you are not defining this language at once for all inputs either. That is what you wrote as C is defined in stages, first defined on 1-bit string, then on 2, and then so on.
Right, no, I think Shreyas's question was maybe more along the lines that what if you give like an invalid description of x? So for example, if the description of x is such that you're actually querying more than x minus 1 times. Like, so say for example, your description is you just keep querying x. Querying C, x many times.
Second condition is about length, right?
Is the number of queries you're making to C. So it is, of course, it's relating the length of the input to the number of queries you're making to C.
So why queries and length are related?
It's just a definition. I mean, in general, it's related because the description of the circuit sort of puts a limit on how many gates you're applying, right? Because normally you think of it as, a gate and what qubits the gates act on it. That's a fairly general description. So if you have such a description, then the length of the string already bounds the number of gates you can apply, and therefore the number of queries you can make, because you're treating a query as application of a gate, right? In a sense.
And when you check this condition, then this is also at the, so this C in V, this,
C in V.
that will also, I mean, that algorithm will also query on inputs whose length is less than mod.
Yeah, so this V, because of condition 2, will only query C at lengths less than n, say for example if the input, right? So it's okay, because you're describing the value of C on n bit length now. So it's assuming that n minus 1 has already been described. Any other questions? Yeah.
Maybe in point 2, the main idea isn't that it runs in time at most mod x minus 1. The main idea is that it just queries C on inputs of then 1 to mod x minus 1. Like, I don't know how time.
It's just the number of queries. It's a consequence. It's just a simple way of stating that you cannot make more than x minus 1 queries.
But even if it did, it won't. Would it matter?
Even if it did, if it had more time, it could make more queries, right? Potentially. You're saying that it suffices to bound the number of queries as opposed to the runtime, right? That's what you're saying. That's probably true, yeah. No?
I was thinking something else.
Okay.
Saying the condition should have been whatever is there in the norm.
If I was like the fact that it queries C on this inputs of then 1 to size of x minus 1,
Mm-hmm.
that is probably enough for the recursive case.
Yeah, it probably is, yeah.
The time, like, number of queries might not be.
Right. Yeah. Number of queries might not be an issue, maybe, yeah. No, that's true, probably, yeah. I think it's just a consequence. I think it's just trying to keep things straightforward.
Also, like, as a silly point, like, if your size of x was just 1 bit, then it won't satisfy condition 2. But you could have a 1 bit verifier that satisfies 3.
Sure. I mean, these are all asymptotic statements. You won't worry about. Yeah, these are all scaling things. Yeah. I mean, in any case, all of the arguments are going to fail on constantly many or finitely many inputs. It's known to. Okay, so that was the. Okay, so NB2 is clear, right? That the U bar being used is different from the U that we had as input for the problem. All right. So now we're going to look at section 5.2, which says promise BQP is going to be the same as promise QMA. Relative to. So this part kind of seems very surprising, right? Like, it's not very clear to me that if you have these two oracles, then somehow you don't need the witness. You can somehow just do it in BQP. It's very, very non-trivial. So let's see how they proceed. So they start with a lemma that says acceptance probability of a quantum query algorithm viewed as a function of unitary transformations used in the query is Lipschitz. Okay. So if you have a quantum query algorithm that's, you view it as a unitary transformation, as a function of the unitary that it's querying, okay, then this function turns out to be Lipschitz. And Lipschitz, remember, was the condition that so you change so there's f of u, right? That's some value. So you take the difference of f of u, and it's at most some value times the norm of the, right? So that's what we're going to show now. Okay, so that's lemma 28. So let AU be a, okay, let's just write, be a quantum query algorithm that makes T queries to a unitary U in a set of unitaries of dimension D. Okay. And then you define f to go from the set of unitaries dimension D to a set of reals by the following function. So f of u is defined to be the probability that the query algorithm uses u and outputs 1, right? Then f is T Lipschitz in the Frobenius norm. Okay, so that's the lemma, and here's the proof. Okay, so suppose that u minus v, the Frobenius norm, is at most d. Okay, this implies that if I do a direct sum, even then the Frobenius norm stays the same, and also if you do identity O plus u dagger minus identity O plus b dagger f also d. Right, basically the identities just cancel, right, because you're just doing a direct sum. When you take the difference, they'll cancel, and so you just have 0 appended and you're taking the difference. Okay, and recall these are controlled, control u and control u dagger, control v dagger. Right, this is something we saw. Okay, and then so lemma 9. So recall this was saying what? It was saying that if we view the unital channel or the unitary channel corresponding to u and v, and we take their diamond norm, okay, then this turns out to be upper bounded by twice the fidelity between the unitaries. Okay. Now if you do it naively, you get some exponential factor, but there's a clever proof that shows you that you can get the bound. Okay. So using this lemma, we know that. So we know that you also have a bound on the diamond distance, right? Because you have a bound on the fidelity. So that the diamond distance between control u and similarly control u dagger is at most 2d. Okay. Okay, and now by the subadditivity of the diamond norm, on the compositions, as superoperators or channels, this implies that a to the u minus a to the v in the diamond distance is going to be at most 2t times t, right? Because the algorithms are making t many queries, and that is essentially as best seen as composition of t many unitaries, and the diamond distance is subadditive, so you get to td. Okay, and by fact 7, which was that the trace distance between a row and b row is at most half the diamond norm between a and b. Okay.
AU and AV, the other part of the circuit could be different, right?
Other part of the circuit, yeah. But like the algorithm is the same. The only change you're making is to the oracle being queried.
So this means the circuit is same, only the queries are different.
Yeah, the oracles are different. So these are basically, so it's going to be some circuit, and it will have some gates replaced by u, right? So you keep everything else the same. You replace the gates that were u to v.
So other set of queries.
Yeah. Okay. But then the whole thing you can view as a composition of u's and v's. U's being applied many times. Okay. And then, okay, so we already have a bound on the diamond distance. This so fact 7 relates the trace distance to the diamond distance, and the trace distance is essentially this object, right? Because it's just making a measurement and seeing whether you get one or not. So by using that, we have that f of u minus f of v is at most t times t. Is that okay? And that was the condition for being Lipschitz in whatever norm one is using. So if you assume that these things are close in that norm, the f's should also be close by t times whatever that value was. Right. So basically it should be t times the Frobenius norm. Where is it? U minus v. Frobenius. I mean, this is actually equal, but whatever. So that was the condition, right? It's not quite equal actually. Maybe I should just put.
Just write the final expression. Let's see it and.
That's the Lipschitz condition, right? Okay, so that completes this proof. Okay, now back to the so this was just a technical statement that's going to be helpful later.
This is strange that diamond norm doesn't have any dimension factor.
Yeah, it was coming from this observation, right? Where did it go?
Yeah, you wrote lemma 9.
Yeah, so the relation between the Frobenius norm and the diamond norm doesn't get that exponential factor. So that's the magic step that we did not prove. Otherwise you always pick up when you're connecting Frobenius and diamond, you will pick up some exponential factor. Yeah. So that's why you're not getting it. I guess that would probably crucially depend on the fact that you're looking at unitaries. So I suppose for arbitrary channels this would probably not be true. Okay. Okay, and then the story is that the next lemma that we look at, it extends lemma 28. Lemma 28 is, okay, the one that we just wrote down, to QMA verifiers. Okay, so what we're going to do is we'll think of V as a QMA verifier. Okay, that receives psi. Okay. And the lemma is then going to say that the max acceptance probability of V is Lipschitz. So far it didn't have any input, right? We didn't say that this algorithm takes any input. Now there's also going to be the input, and then we're going to say that even if you maximize over the input and you consider a similar function, then the function is still going to be Lipschitz. Yeah, I think things will make a little more sense once we define the BQP machine. Sorry, the BQP whatever verifier, which doesn't take a. Yeah, basically when we define the BQP algorithm for the QMA verifier.
Inside this diamond lemma 9 thing, that u dot u diagonal, so was it a state or what was it?
Yeah, this is just acting on a quantum state, right? Like a density matrix.
Then why the diamond norm is within two?
Channels, right? It's between two channels, so it's just describing the channel like that. It's just notation.
But this is a state where you applied on the state. So you wanted to write u minus v diamond norm.
I think.
No, it's just a channel. It's just viewed as a channel.
No, but the output is a state.
That is true for a channel as well, right?
Yes. So when you write the diamond norm, you write between channel n and m.
So that's why I'm writing the channel, right? I'm not writing the input. Like when you write the channel, it takes as input something. I'm not writing the input. I'm not
It's
saying.
just like u minus v.
It's not u minus v because u minus v are unitaries themselves.
Yeah, so the channel that is.
Yeah, exactly. It's the same thing. Yeah, it's just notation. Like you could write u minus v and understand it as channels instead of unitaries, but to not just to not cause confusion that you're writing it between Hermitian matrices. Oh, sorry, unitary matrices. Yeah, there's nothing very deep. It's just channel. That was your question, right?
Yes.
Okay.
You can write curly u as a unitary channel that applies u by conjugation.
Yeah, but they're using curly u for something else because they're using curly u as a sequence of. Right. Yeah, it's just notation. Nothing very deep. Yeah. Exactly. Okay, and you were saying something? No. Okay, so then, so let me write the lemma then. Oh shoot, I forgot to complete the story. So the story is, so the lemma says that the max acceptance probability of V is Lipschitz with respect to the queried unitary. Again, I think in the Frobenius norm. So the statement is as follows. Let the verifier, querying u and psi be a quantum query algorithm making t queries to u, so it makes at most t queries, and takes psi as input on some fixed but arbitrary number of qubits. Right? Number of qubits. Okay. Define f as follows. So f is a function that goes from the set of unitaries to the set of reals, and f of u is like I said, you maximize over all states psi, and you look at the probability that the algorithm outputs 1 with psi as the input, right? So if you do this, we'll see that f is t being the number of queries, so it's going to be t Lipschitz in the Frobenius norm. Okay. All right. Is the statement okay? Right. So for the proof, the first note is that f is well defined because, yeah, this actually I don't understand myself, so maybe you guys can help, of the extreme value theorem. So I guess because of the supremum they've written max, so I guess somehow you have to show that the value can be achieved when you're maximizing. But yeah, this part I don't actually fully understand. But for the moment I'm assuming that it has to do with some convexity like argument. So you can attain the maximum. Okay. All right. And then we define f sub psi as follows. So f sub psi goes from set of unitaries.
It will lie between 0 and 1, so maximum will be defined, right? If it was some diverging thing, then you will worry.
No, it could still oscillate, right? There's no guarantee that you actually converge. Could be that for many different.
Oscillation is not a problem because you are taking maximum, so maximum will still be defined even if it is oscillating.
That is true. Yeah, but it's probably the same, right? As a sequence may not converge if it's even if it's bounded, right? Like you might not. So, for example, you might not reach 0 if it's 1 by x. Like there's no x.
And maximum does not care that whether something converges or not. It has to converge inside the set. And here the answer will be between 0 and 1.
No, like for example, 1 by x, right? This is going to be, there's no x for which this would actually give you 0. If you're minimizing, right? So if you say.
If you are minimizing, if your set is R, just R without infinity, then you are right. So
Here the set is psi, the set of states, that's what you're maximizing over. That is not a concern. This is just 0, 1, right, in this case, because it's a probability.
but maximum is
Like the set over which you're maximizing, that is a.
no. You would check the value in the range.
No, the argument has to exist, right? I thought max was that there has to exist some psi which actually achieves the supremum. I thought that's what max meant. Maybe I'm wrong. Let's not get distracted. We can look at these details later. Let's continue. You can tell me later if you figure it out. But okay, so we're defining f of psi as this. So it's just the verifier acting on some fixed psi. Okay, so this psi is the quantum state. The second note is that fu, right, is in this notation just the max over psi of f psi u. Right, I've not done much. I've just written psi explicitly as f sub psi, and then I'm taking the max. This is fine, right? Okay. The third note is that lemma 28, right? That actually applies to f psi, right? Because psi is a parameter, a fixed psi. Then I can run the lemma. So the lemma says that f psi is T Lipschitz for every psi. This is fine, right? Because the oh no, where did I write? Did I remove the lemma? Okay. You'll have to check the statement of the lemma, but okay. And now, so now we let uv be two unitaries, and suppose that psi and phi are such that f of u is f psi of u and f of v is f phi of v. So basically you're picking the states that actually maximize the function, right? So it's in, but they may not be the same, that's the point, right? So I'm calling one of them psi, the other one phi, and then I can write fu minus f of v as f psi u minus f phi v, which is the same as taking the maximum over f psi u minus f phi v, and then the other way f phi v minus f psi u right? It's very elementary so far. I think the delicate arguments will appear once we have the lemma. I think after this lemma it starts getting more interesting. All right, and now is this fine? I've just written the, yeah, let me, so board work is getting a little confusing, sorry. Is this step okay? I've just written that mod A is basically max of A and minus A. That's all I've done. Okay.
So it is clear that both the difference cannot,
I've not done anything non-trivial yet. It's just
no, I'm thinking that both of the differences are negative, that cannot happen, right?
yeah. Unless it's 0, of course. Okay. Right. So now what we're going to do is now the point is that this phi was basically making fv as large as possible, right? So you were subtracting the largest possible value. So if you instead of phi put any other value, it will only increase this, right? Because you're subtracting something smaller, correct? So that means that I can put an inequality and write f psi here, right? Is that okay? And then similarly I can write f phi here. Okay. All right, and then this is basically what now we're going to use the fact that f psi and f phi are T Lipschitz to get that this object is at most u minus v Frobenius norm, right? Because each of these individually we know is at most going to be okay. So and that basically establishes what, that FU with the max is still Lipschitz because of the bound. Okay.
So this, about this you were right, that this maximum portion, because
Yeah, it's in the proof. It's using that there exist. Sign
because
phi.
if you had any other state which is not pure, and suppose you are thinking that you will get maximum there, it's not possible because of convexity. So any other probability that you can get with mixed state will be lower.
Yeah, maybe that's all that is meant actually. I'm not sure. But yeah, because that basically comes from the fact that it's convex. So it's going to be in extreme. It's going to be in the corners or whatever.
You went to the second last.
This one. So you're subtracting. So suppose this is fixed, okay, for the moment. You're subtracting a number, and you're subtracting the largest possible number here by choosing phi. Had you chosen any other vector, you would have subtracted something smaller, right? So that would be certainly yeah. So if you subtract something smaller, you wouldn't become smaller. So that's just an inequality. And similarly for the other side. Okay. Right. And then oh my god. All right. So now we look at. So this is fine. What is the story? The story is that now we're ready to prove the main result. So the main result is the following. So theorem 30. So it says with probability 1 over U sampled from D, promise BQP with oracle access to UNC is the same as promise QMA with oracle access to UNC, right? So if this is obvious to you at this point, that would be very remarkable, but let's look at how the proof goes. So suppose that pi is the promise problem that we're interested in. Okay. So this in particular means what? It means that by the definition of QMA, so definition 12 I suppose is the definition of QMA, promise QMA, we know that there exists a polytime verifier, polytime quantum verifier, V, where is this here? UC on X and psi with completeness to third and soundness. So completeness probability to third and soundness probability 1/3. Right. So far it's just nothing much other than the fact that it also gives oracles to the verifier. Right. Yeah, maybe actually I can write this over here. And without loss of generality, one can amplify the completeness probability of V to 11/12. We'll see why these numbers are used. And the soundness probability of V to 1/12. Okay. Right. So So now let Pn, okay, we have time, good. So let Pn be a polynomial upper bound on the runtime of V on input x of length n. Okay, so suppose this is the upper bound on how long the algorithm would take to run, regardless of what the input is, as long as it's of size n. So we now describe a promise BQP algorithm, okay, and this is where things will get interesting, such that with probability 1 over u, A computes pi on all but finitely many inputs. X in the domain of pi. Okay, so this is the magic step. So let's try to understand what the construction is. Okay. So here's the construction for A U C X. Okay, so what is the construction? So first let D define, let D be as follows. So it's the log of 3, 4, 5, 6, and it's not just 3, 4, 5, 6. It comes because of multiplication of some numbers. At first I thought it was just for fun, but it's not. Okay. So this is going to be sort of a threshold, and now what we're going to do is, for each n in the set of numbers 1 to d, A is going to do the following. Okay, so A performs process tomography on each un, and produces an estimate u tilde sub n such that the diamond norm between the estimate and the actual unitary is at most 1 by 6p. So let me write that down.
What's the domain of pi?
So pi, remember, is a promise problem, right? So it's not defined for all inputs. So it's basically just the set of x's for which it evaluates to either 0 or 1. So basically all inputs for which the evaluation is non-bot or non-perp. Okay, so domain is x such that pi x belongs to 0, 1. Okay. All right. So it performs process tomography to get u tilde n minus u. So the diamond norm is at most 1 by 6 to the p. Sorry, 6p for all n. Okay, with probability. So for all n, as in the n's that we restricted to, with probability at least 2/3 over the randomness over here. And we're going to denote these estimates So far we haven't done much.
We assume that it can perform process tomography.
Yeah, because d is small, right? So d is like log of poly, so it's you're looking at log n many bits essentially, like polylog n many bits. And for polylog n many bits, even if the process tomography procedure is exponential, it would just amount to polynomial amount of work, which you can do in the yeah, so the whole thing is basically an exercise in essentially substituting actual u's with doing some part of it locally. So you're given a u and you do process tomography, and the remaining part you replace the best u with the average u, which is what the language is going to do. Oh, so it's so tomography is right, is yeah, so process is for a process. So you have to find the description of a unitary or the description of some channel that behaves the same way as the black box that you're given behaves. So tomography is you're given copies of states and you have to figure what the state is. Here you're given Oracle access to some process, and you have to like run it on different inputs and come up with the description of this state. And we want that these are like standard things.
So what is UN?
UN is the this one. Yeah, that's the Oracle, right? You have access to the. So this U itself was, remember, a sequence, right? And each of these was sampled from mu to the n to the n, right? Like there was a direct sample.
You are not making any connection yet. Still with the promise QMA that you want. Because how do I make sure that this unitaries that are used by this promise problem are of index that is polylog?
I'm just describing the. I'm not done describing this. This BQP machine, right? So my claim is that this BQP machine is going to do essentially just as well as the QMA machine with the witness.
Yeah, exactly.
So I haven't done that yet. I've just described one step of the procedure. That step is to construct this estimate.
So I'm just saying the first step, it will not be able to perform if this D doesn't satisfy this equation.
Yeah, but like I said, right, this D is a log of some polynomial, so it's going to be polylog.
Yeah, so it will only have the process tomography for UNs, which are.
Yeah, where n is at most D. Yeah. I haven't said anything beyond this. You're correct. I'm not saying that this does the job, right? Of course. Otherwise, you have to do something more, of course. Okay. All right. Where did I write it? Yeah, sorry. I got lost in my page. Okay, so that's the first step. The second step is that A constructs a description of X. Okay, so this is where we start using the classical oracle. A description X of a quantum oracle circuit W when U bar C, okay, has the subscript U tilde, okay, where X and U tilde, which is the estimate, are hard coded into the circuit. Okay, so that's one, and the second one is psi is the input to the circuit, and U bar and C are accessed as oracles. Okay. Is this fine? Right. So how is this circuit defined? Okay, so the circuit is defined as V U C X.
What is about U-bar? U-bar is U-bar and CR?
So remember the definition of the language C, right? So in the definition of the language C, X was supposed to describe a quantum algorithm that queries U bar C and takes as inputs I. So it's exactly of that form. This part is hard coded into the description, right?
Yeah, what did you write? U-bar and CR?
Accessed as oracles. Yeah, sorry. Yeah, sometimes I try to. Yeah, I wish I could write twice as fast. It just takes so long. But okay. Or at least, yeah, then I would write neatly. One or the two, at least. Okay, so then UCXI, sorry, what is the definition of this W? So this the definition is as follows. So you take the verifier that we had here. Okay, so we are assuming that there exists this verifier. So we're going to modify this verifier. So you take this verifier and you do the following, except for each n in D, queries to un are replaced by un tilde. Okay. So whenever it does queries to un for n within D, you're going to substitute it with the estimate that you have. Okay. And for each n which is greater than D, okay, so let's just say for each n greater than D, queries to un are replaced by those two u bar n. Okay, because it was supposed to access the oracle that was actually given, but the language L, remember, was independent of the oracle that was given. So what you're doing is you're just asking it to use whatever oracle the language locally samples. Okay, so that's the definition. Okay, and X is I think the problem instance you're solving, so you have to get that. And psi is the witness for the original thing. Right.
So U bar is actual oracle and U bar is.
U bar is sampled by the language independently, essentially, for the purposes that we were describing, right? Like, because it said that on an average. So U bar is basically to be thought of as an averaging procedure. Because the language said, right, like, so the language accepts if on average the probability is greater than half or less than half.
Yes.
So
on like polylog bits, when the index is polylog, then it's doing actual thing and doing process tomography. And on other things, it's replacing by something.
yeah, basically replacing by an average of what you're supposed to do. And then the whole point in the remaining argument would be to show that these substitutions do not change by the properties of the Haar measure. Making these substitutions does not change the success probability. So it's it's pretty crazy. I don't know how we thought of it.
You just do good stuff at polylog and then rest doesn't matter.
Yeah, no, it's pretty insane. I have no intuition for how it's done. Apparently, it's related to how. Let me not say much more. It's okay. I don't want to say wrong things. Or let's say at least the construction is step 2 of the construction is fine. We have 10 minutes. I think we can do the third step of the construction as well. So let's do the third step. Alright, so the third step is as follows. So, oh shoot, I think the third step is it's essentially done, right? So A queries C on input X and outputs the result. So it basically asks the language to give it the evaluation, right? Is that okay? Louder, louder.
Where is the instance? Like problem instance. Like I thought it would query W or something.
Yeah, I think there may be like a little bit of an overload in.
Because X is the problem that we're trying to decide, but C takes some description.
Yeah. No, you're right. I think maybe the notation is a little bit because whether this description X and this X are the same is a little bit strange. Maybe it's just overloaded notation. Wait, let me check. Because I also did it in the morning, so I may have messed up. Double check.
The first X is what is this?
Yeah. So in my head, like if you call this X prime, then you're sending this X prime, but then it also doesn't make sense because you have to have yeah, it's probably X prime. I think that would make much more sense. I think it should be X prime logically, but let me just double check. Yeah, I think it should be X prime. In the note also, I mean, in the paper also it uses X, but that doesn't make as much sense to me. The whole point is basically to have this W run, right? And the way you run W is by giving the description of W. So what label you call it should not really make a difference. The important thing is that W itself is encoding X, which is the problem instance on which you want it to run. All right. So this is fine. So that was the third step. So this is the construction, okay? So you can sort of see what is going on a bit. And let's see what the paper says here. So now the paper shows that for any X in the domain of pi with high probability over U, A correctly decides pi on X. That is, probability A UC X equals pi of X is greater than 2/3. Okay. Right, because for the yes instance it's greater than 2/3, and for the no instance you have to say that it outputs 1 with at most 1/3. It's equivalent to saying that. All right. Okay, so now we have some notation. So we're going to define this notation, f u tilde u bar. Okay. So given a fixed x and a sequence of unitaries, u tilde, so it goes till t, and u bar, bar, this goes from d to the this p. What was p? It's probably the number of queries or something, right? Upper bound on the runtime, yeah. So it's at most the number of queries you make, right? Okay, so you do this, and then you define fu tilde u bar to be the following object. You define it to be the max over psi. This is just notation, okay? We're not doing much, but it's useful notation. for the problem. Let me write it in the next line, otherwise I'll not be able to fit it. So f u tilde u bar is defined to be the following. So it's the max overall state psi probability w u bar c x u bar psi is 1. I think I messed up a little bit. One of them should be a tilde, probably. Which one is tilde? I think this one is tilde. Okay, so basically it's the same as the W machine, but you're maximizing over all possible witnesses. Is that okay? So that's just the definition of what f is. And then also note that using the same notation, the algorithm A outputs 1 if and only if expectation of u bar comes from D and f of u tilde u bar is greater than half. Okay. So this is essentially just restating how we defined the language, right? Because A is going to essentially output whatever the language outputs, okay? And the way we define what the language does is we said that, you know, it does whatever u tilde and x are, that's fine, but it samples u bar uniformly. Uniformly, I'm saying from the distribution D that we defined for the oracles, right, which was the direct sum of 2 to the n unitaries. So is that object, except that I'm now, so you know, in f there was u bar, but u bar I'm now sampling from this D. So if I take that average, if it outputs 1 with probability greater than half, then the language was defined to be 1, right, accepted, and 0 otherwise, right? Where did we define the language? Yeah, so if you look at your notes, the third condition was, you know, so we can quickly recall. So this is recall in the definition of C. Okay, the third point was that you accept, or you know, output 1 if expectation over u bar from this distribution, you take the best witness, probability output 1, and V was the description, right, of the input. Okay. So if this thing is greater than half. Okay, so if you check your notes, this was the condition. And now you can directly inspect and check, right, that by using this little f notation, all we did was we left the u bar explicit, right? We didn't specify it, and now we're saying that if you take the expectation over the distribution, which is exactly what that expression says, if that output is greater than half, then the output of the language is 1, which is exactly what the output of A is. It's the answer that C gives. Is that okay? Are you getting?
This was only for log.
Huh? What? It was for log many. What was for log many?
For each n in D,
Yeah.
where D is some log of size of x.
Yeah, that was used implicitly, right? That's hard coded into the description. You then send the description. So I'm not writing that. So you know, the thing that I was writing as subscript, I've written it explicitly here. Sorry, I changed the notation. It should.
So the language like blows up the number of results from log many used till how many of you is that thing? Yeah, then
If
you
it-
solve it.
No, you've not solved anything.
like,
The problem is still of size n, right?
In part 2, you write, right, that what happens if n is not empty.
So you're defining a new machine, right, for C, and the way you're defining this new machine is that you've done some pre-computation that you could, so that would only be like for log-sized unitaries, right, because those are the ones you can learn in polytime. So you pre-compute them, and they are coming from the oracle that you actually knew. Okay, so you hard code it into the definition of the verifier. Okay, and then you query the language, and the language is going to replace all the subsequent queries that you could not pre-compute with average computations and give you the answer. And here it's just notation. So here it's just saying that this is the part that you pre-computed, and this is the part that was supposed to be computed on average by the language itself. And then this statement is just saying that if you do that, there would be some acceptance probability because the witness still had to be specified, right? So that's why you put the max here. And then for the best witness, if on an average you're getting greater than half, then C, remember from this condition, said that that description of verifier, that such a circuit was in the language. And so this is just saying that A is going to output 1 if and only if this condition holds, which is just the condition. Okay. All right. Oh shoot, we've exceeded our time. Yeah, maybe it's a good place to stop. We can continue next time. Okay. Thank you.